right, so welcome everyone to the next live stream where we try to improve our current 1 billion row challenge in C. Now, the last time we left off with our pretty simple baseline solution that took around 5 to 6 minutes to execute. Now, today we want to make this work on multiple threads. We want to fix a bug I noticed in the linear probing code of the record map we have implemented, and maybe add some hashing. Okay, so let's get right to it. Where did we left off? So we had our entry point for each thread, and as you can notice, we also have a different font today, so this might be easier to read. I don't know. Yeah, let's delete that. We have added a profiler, and that's that. We also, we can define scopes, stuff like this. And in the end, we print our record to see whether this matches the original or the correct min, mean, and max temperatures from the baseline solution the GitHub provided us with. Now, I was wondering, so we have a bunch of to-dos now. So to-do number 1 for this is fix linear probing code. This is the first one because there is a bug in there, and it only works because we return 0 as our hash right now. Then add debug information to the probing sequence code. We want to know how long our average median probing sequence is. Now, maybe the average is not what we want, but rather the median or something like that. I don't know, because the length of the probing sequence basically determines how good our hash is. And maybe add a hash function to the insert record code, and maybe add RDTSCP to the low-level profiler. Okay. So first and foremost, we have made a we have created a bug here where we just start at the index that's provided by the mask of digest. So this can be from 0 to map size -1. And then we just run and walk through the entire array until we hit the last element. Now, if our hash, for some reason, returns the last element, or the index to the last element, we don't walk the rest of the elements. So, so there are two things we can do. We can pull this so we could either do 2 for loops starting at the index and going to the end and going from 0 to the index. This is one option. We can also pull this indexing into the loop. So the probably easier thing is to pull the indexing into the loop, but it may not be the most efficient thing. I++, this index does not exist anymore, and then we say u32 index is equal to digest plus I, and then we mask off the map with the map mask. Now the other solution obviously would be to pull this loop out. I don't know how expensive this would be, but maybe the compiler does it. I don't know. I don't know if the compiler can do that, to be honest. So let's, yeah, I can show you the other solution as well. Else and if. So let's pull this again. Let's say u32 mask digest is equal to digest and map mask. And now we start at, so let's say u32I is equal to mask digest. We go to the end of the map, or let's say index. We go to the end of the map. And then we remove this. We have to then do it a little bit differently. We have to like say, okay, this is insert record return. And then we have to, instead of breaking, we make a goto insert record return. Goto insert record return. And this way we only get to the second loop if and only if we haven't found the candidate in the first loop. And here we start at 0 and go to the masked digest. I think, yeah, this should work. So we can also change this to go to insert record return and go to insert record return. All right. So 2 versions. This is already the first to do that we had to fix. So let's put an X here. Now the second one is add debug information to the probing sequence. Oh, no. Also fix the implementation so that we can support multi-core code. Multi-core, more than one thread. So at the moment in entry point, we do not scan the chunk that has been assigned to the current thread for the first new line. So we can end up in a situation where our first few bytes are like a city, Yinshuan, because our splitting does not really consider this, and then we hit the new line. Now, maybe like this. Like this is an incomplete city, or we can even end up on this. So our chunk starts with this, and if we call the parsing function, we get an error. Or even worse, it fails silently because it doesn't start. It starts at a string, and it just takes the partial string, or we insert twice. So all of these things can happen then. So to avoid this, if we are not the first thread, we want to scan for the first new line in our chunk. And of course, we want to scan for so we want to scan for the first character that's not a new line. How do we do this? Well, it's pretty easy. we have the chunk adder. So the problem is we don't really know how far we can scan. Or do we? Well, we do. So chunk to end. Chunk to end is equal to file size minus chunk start. So file size was the global variable. Chunk start we calculated by multiplying lane IDX times chunk size. And therefore, no, this is chunk end. Chunk to end. Now we want to start at chunk start. And then we want to say find character. First new line. Find character in chunk adder with chunk to end, chunk start to end. And we want to find a new line. So this is the first new line. We should set chunk adder to this, right? Where do we set the cursor? Cursor is equal to chunk adder. So this, no. So end cursor is this. Cursor is equal to first new line. But this, again, we should only do this so let's set this to chunk adder, and if our lane IDX is greater than 0, if we're not the first thread, we want to do this and set set cursor to first new line. Okay, and we also have to adjust the end of the chunks, and we have to adjust our end. So end cursor is also not correct. Let's pull end cursor out as well and put it here. And here we scan. So let's not make this a U32 but a U64. U64 chunk end to end is equal to file size minus chunk end. And what we want to do is find character. Now this could be 0 because our end is the actual end. So if chunk end to end, let's set U8 star and cursor equal to chunk adder plus actual chunk size. I think that this was the initial thing. And then chunk end. Yeah, I think this is correct. So if this is greater than 0, Then we do find character from end cursor to chunk end to end with a new line. This will be the end cursor. Now, is this correct? So our chunk end is this. Maybe we want to subtract, we want to add 1. I don't know. Do we add 1 and then just don't do it? And do it like this? Let's see. Let's see how it works on a single. Oh no, okay. Yeah, we have to test this out. Build. Let's build it with -g. And 1 second. I obviously haven't started the debugger. All right, so here is our debugger. We don't need this. Let's see what happens. So chunk start to end. If this is 0, okay. Should work. I mean, let's just break also. No. Build. Oh yeah, start 1. Start TSC. We don't need that. We don't need that. We don't need all of this. All right. And let's break here. Let's launch. Okay. Continue. Okay, lane IDX is 0. Chunk end. Chunk end to end is 1, which is expected. End cursor. Okay. So this is the complete end. So what if we subtract? Okay, let's also subtract 1 from the end cursor. Is that okay? So the thing is, end cursor. Let's subtract 1 from this. So this is kind of the last byte. Let's say this is last byte. Last chunk byte. Last chunk, last byte. Chunk end to end. And then we want to set the end cursor equal to last chunk byte plus 1. I think that is correct, but I don't know. So let's rerun. Alright, lane IDX is 0, chunk end to end is 1, last byte is the new line, this is correct. So last chunk byte is equal to find character, this returns this, and we get our correct end cursor. Now if, for example, we would now say end cursor minus chunk adder, we should get the file size. Now I have no idea if this also works on multiple threads. So for one thread, it now works. Hopefully. If we increase lane count to 2. Okay, let's see what happens. I wonder if you can also freeze threads. Can you freeze threads? Here, somehow. I don't know. So what lane? We are on lane 0. Now we're on lane 1. Okay, so chunks start to end. Chunks start to end is this number. Okay. First new line. So let's look at cursor. Oh, we also yeah. Let's look at cursor. So cursor at 10. Can we like display this as a oh yeah, here. Cursor. Here. The cursor starts at the semicolon. Now that's bad, because it should start at this H here. Yeah, so find the first new line. So first new line is exactly this. And then it has to be first new line plus 1. First new line plus 1. Okay. So maybe this works. I don't know. Now each individual thread builds its record map. Let's quickly set lane count to 1 again, and just for a basic estimate, see how this performs. Build 1 BRC. Let's just let this run. Put it to G again, and I don't know why this is happening. Whatever. 1 second. Right, there we are, back again. 1 BRC. So the thing is, each thread now builds its own list of records or record array. Now we have to join them together. The problem is they all live inside they all live inside these functions. What we could do is, what could we do? So we could sort of we could create a function join record maps. Now it takes in a record star star or record. Did we specify the type of the map? No. Join record maps. Okay. Oh yeah, we forgot to do it with time. Record maps. And we also know how many of them there are. What does this return? I'm not sure. Should we do this on a single thread? Should we do this on multiple threads? I mean, the joining could be done on multiple threads. Yeah. But whatever. So let's just say we have now lane count. We want to join the lane count record maps. Now, how do we do this? We have to go ahead. We could join it into the first one. Into the first record map. Now, the first record map, let's say record star first record map is equal to record maps at 0. Okay. And we should probably make this a record map type in the future, but let's not bother with it for now. So first record map, we want to iterate over all of its buckets. U32 index, U32 record index 0, record index is less than map size, and record index plus plus. All right. Now our record star record is equal to first record map at index record index, and just get a reference to it. Now we want to iterate over all of the remaining record maps. How do we do this? We just go through map index 0, map index less than lane count minus 1, and map index plus plus. Now, the other map, record star other map is equal to record maps at index map index plus 1. And we now want to try to find the same record in, now I don't know if this is the best approach, but obviously it isn't. But we just want to find the same record in the next map. So let's say map k is less than map size, map k plus plus, and record star other record is equal to other map at map k, and that's that. Now we want to compare name match or city match is equal to string equal what's the definition of a record again? It's a string equal, let's say this is mem equal return And do we use string equal? Yeah, we use it here, right? Mem equal, and let's define string equal u32 string equal of two strings, string A, string B, and we just call mem equal u32 result is equal to mem equal a dot pointer, a dot length, b dot pointer, b dot length. Return result. Okay, so string equal, we can now call in the city string and this our city name. We don't have to pass all of this stuff. String equal. Do we use it anywhere else? Mem equal. String equal. I don't think so. Okay, yeah, so that's string equal. Yeah, this is not a comment. This is very confusing. It's just if deft out. So same thing here. My editor is a little bit slow. So city match is record. Did we call it city name? I didn't remember. And other record city name. So if we have a city match, city match. Let's see. If we have a city match, we want to join the two records together. So we want to say record min temp is equal to min of record min temp and other record min temp. Then max temp is equal to max temp record count plus equals other record dot count. No, count. Now we only want to do this if record if this record is set, if record count greater than 0, and also here only if other record count is greater than 0. All right. Okay. So and record mean temp plus equals other record mean temp. Yeah, this is probably also very inefficient. So let's also add this to our profile code. And as we can see, okay, our code now takes 6 minutes, and we indeed report the correct thing. So rg baseline.txt, no, Yinshuan That's bad. Yeah, here, Yinchuan, negative 47.8 is the min, 9 is the mean, and 59.4 is the max. Now, as you can see, we have the exact same answer. Now, with this, we should probably be able to join all maps together and do the operation on multiple cores. Now we have to be a little bit careful because we have to wait for all of the cores to effectively finish their chunk processing. How do we do this? Well, on Linux we have a nice function for this. Oh man, I forgot to switch scenes. No. Forgot to switch scenes. Okay, let's see again. So this is our join records map. So basically we have the first record map, which we use to put all of the results together. And then we iterate through all of the other record maps, searching for that record in the record map and then joining the two records together. Makes sense. But only if the cities match. Okay, so the thing is, we want to do this at the moment just on one core. Now we have to wait for all threads to finish. All threads have to successfully put all record maps together on their chunk, and then we can start to join them. Now, in Linux, we have something like a pthread barrier wait. And what pthread barrier wait is exactly what this man page says. The pthread barrier wait function shall synchronize participating threads at the barrier referenced by barrier. The calling thread shall block until the required number of threads have called pthread barrier wait, specifying the barrier. Now, first we need to initialize a barrier. This we do in our main function. Pthread barrier init. Okay, pthread barrier init takes a barrier. Okay, that's all right. So let's initialize a barrier. Pthread barrier t as our barrier. And I mean, we could make this a global variable, but we can also put this into the thread context. Pthread barrier t star barrier. Okay. And in context, we set the barrier to the reference of the barrier. Okay. Now we just need to call pthread init barrier. Oh no, barrier init. Pthread barrier init with the barrier, and we are good to go. Okay, so here, after each thread successfully processed the chunks, processed its chunk, it has to wait for all of the other threads to also have processed their respective chunks. Now, this we can do with pthread barrier wait. Now, as you can see, pthread barrier wait takes in the barrier. Oh no, okay, init, pthread barrier init, pthread, oh my goodness, barrier init. Pthread barrier init also takes an account, which is just the lane count. So it needs to know for how many threads it has to wait. Init, yeah. So, and this is our lane count. pretty easy. Pthread barrier wait. Now we wait on our context barrier. This synchronizes all of our threads. And then what we do is we check if our lane index is 0, and then we join record maps. Now the only problem we really have is that we don't know where the record maps are, because they are allocated from inside the individual thread allocators. Each thread has an allocator, and it uses its arena allocator to effectively to allocate their records. As you can see here, arena push array 0 with record and map size. Now, what we could do is we can add a global variable here, which is a static record star record maps lane count. And then join record maps really doesn't have to take anything in. And static, let's just put that on top of here. Yeah. And what each thread now does is it sets record maps at index lane idx equal to their respective record map. Records. And then we synchronize, and then we join our record maps if we are the first thread. And probably also get the mean on our map. And also, if we are the first thread, we also want to print this. Now, does this work? I have no idea. We have some problems. Too few arguments. Oh, it wants. So init pthread. It has some attributes. We don't care about the attributes. Barrier init. Let's just set them to null. Let's see. String equal. Here there is something missing. Also here and here. Okay, now we only have warnings. Yeah. So that's pretty neat. Let's see if this works. Let's just run it and see what happens. With a single thread. Now with a single thread it takes too much time, right? Let's also do something. Let's say so I have an idea. We could do I still have the code here? Do I still have the code? Okay, I still have it. Let's see. So you could do calculate, no, create measurements .sh, and let's just do 10 million. So we have a, now we have a smaller file, and calculate average, I think it was baseline. calculate average baseline dot sh. Let's see. Let's hope for the best. Let's put this into baseline short or small dot text. And let's go into stream 1BRC. And let's move 1BRC original measurements.text, measurements small.text, and baseline small dot text here. Now, what happens? So let's measurements small dot text. So this should now only be working on 10 million. So it should be significantly faster now. Did we build? I don't think so. I wonder why it still takes this long. Okay, so now 25 seconds. Okay, as you can see, join record maps. Yeah. Takes no time because it joins no maps, right? That's pretty obvious. Now let's increase the lane count and see. Well, first we have to check whether we actually get the right result. So in small, baseline small, yin, shuan, 32.5, 32, yeah, see, it's not the correct result. Oh, Luanda, negative 16.8, negative 16.8, 25.9, 25.9, this seems correct, and 66.2. You know what? Printf, let's just do this for each record. So for and U32 record index less than map size, record index plus plus. This is the record. Add record index. And let's build it. Let's time it. Let's wait for 20 seconds. So yeah, as you can see, we spent all of our time in insert record. Oh, there's a bunch of zeros because we have to skip. So only if record count is greater than 0. This now prints all of the records that don't have an entry, which is not desirable. Let's see. So now you can see, let's check another one, Zurich, build, no, baseline small, Zurich, I think it's at the very end. negative 33.7. Yep, 9.4, 9.4, 49.1. Where was it? 49.1. So this seems correct. That's good. Now, let's go wide. Let's increase the lane count. Build. In our build, we compile it with G. Let's compile it with O3 and change it to 1. Let's just get an estimate of how long it will take. All right, so 3.7 seconds. We spent again all of our time in inside record. And yeah, let's go into 2 lanes and see if it's still correct. Now this was already in 2 seconds. Let's see if Zurich 33. I didn't remember it. It was at the end. Negative 33.7, 9.4, and 49.1. So it seems to be correct. Let's go even wider. Let's go 4. Yeah, 1.2 seconds. Okay. Yeah, but this is only 10 million records, right? So let's also do it a little bit differently. Let's not print this. Where is it? Printf. Let's do something like if def 1brc debug. Let's only do this if this is defined. Build dash d1brc debug. And here we do an fopen and an fopen on output or result.csv. And we do an fwrite onto file star handle. We do an fwrite on the handle and we call this city name, then count and min, mean, and max. New line and fwrite fprintf and to handle this. And this is now comma, comma. So this is how we create our CSV file. Let's build it. Macro name must be an identifier. What? Oh. OBRC? Is it because there's a 1? Yeah. It cannot take once. Yeah, and as you can see, we also get 4 profiler reports now. And yeah, in all of the threads, we spent most of our time in insert record. So this is probably the function that we want to look at. Now we already knew this. Profiler report. Let's also print just a new line here. Right. How long does this take in debug? Significantly longer. Okay, 6 seconds. Yeah. Okay, so we wanted to collect some information on how bad insert record is. Now, insert record is bad for mainly, for multiple reasons, but first and foremost, the hash function is obviously pretty bad because the hash function creates all of the collisions. Like, regardless of the bytes we're given and regardless of the length, we always return a 0. Now, how can we improve this? First, we can change the hash function, but again, let's try to measure. Let's try to measure and enable measurement using a debug counter per thread. Like, where do we define these things? Let's say, okay, so if def obrc debug and if we want to collect information on the, like, let's say static debug information, debug info, and let's have a type def struct debug info, struct debug info, and debug info for now. So each thread has this. Let's just say it has a U64 probing sequence lengths and hash hit count, maybe like PB, let's call this PBS, and like total PBS and or PBS total and PBS hit count. And an insert record, I mean, we have to determine how long the probing sequence was. How do we do this? There's probably a way you can do this by using the index, the final index. But we can, I mean, in this case, we can just use I. So let's U32 PBS. Or let's declare I here. And let's say, so if def obrc debug, and if we just set debug info dot PBS total plus equals I, and debug info PBS hit count plus plus. No, we didn't call it debug info. debug info. Okay, then we have that and an entry point. We also want to report this and say printf UF64 average PBS is equal to debug info dot PBS total and over debug info dot PBS count. Now F64 and average PBS. Now, does the average correctly reflect all of this? I don't know. Let's see. Okay, let's run this. And it didn't print it. Why? Why didn't it do it? OBRC debug like, is there results dot? No, results dot is also not there. Dash D OBRC debug. Did I misspelled it somewhere? OBRC. No. It doesn't do it. Okay. Why? Okay. I thought we can just define it like this. Clang define macro dash D. Do we have to do it like this? I thought you can just do it like this. 1. Nope. Why? Oh man, this is weird. OBRC debug. You know what? Screw them. Oh. Huh. It did work, so does it just need an equal? No. If def. If. I mean, is it... Is it really this? What? What is this? Oh, there's a typo. If debug. So this was correct. I just had a typo. Oh, fwrite. Let's just use fprintf. Fprintf. Okay, pbs count. It was hit count, right? Hit count. Fopen with write. Now we should get it. I see. Okay, negative nan. Negative nan. What the heck? But now we have a result.csv. This is nice. Like, that's good. Not sorted or something, but that's okay. 1 BRC. So what is happening with our average PBS? I mean, this should be printed on each thread first. So that's the first bug. Now debug info, PBS total, PBS hit count, PBS hit count. It's U64. Nan. It's all nan. I mean, this can't be the problem. It's not. Okay, fire up the debugger. Why do we see all of these nans? Debug info is undefined. It is defined. Yeah, this is shit. Okay, we can't do it like this. It should be. Where is this coming from? Oh yeah. if this is shitty. If def obrc debug and wrap it here again. So this way we can get some information. Okay, but it is none. So let's go into the debugger and figure out why this is. So let's make a breakpoint here and launch. Okay, now let's look at debug info. Both 0. You know why they are both 0? Because we have put a goto in this. Yeah, this is probably why you don't use gotos, because they cause some shitty bugs. Now we have to make sure that we don't screw this up completely. Let's set a U32 PBSL. Or more verbose probing sequence length. All right, let's here probing sequence or PBSL. Now this let's remove this I, PBSL, PBSL, and PBSL plus PBSL plus this. All right, so this won't work here. So to do this code doesn't correctly identify the PBSL. Yeah, we can also just remove the code. I don't know. Okay, plus equals I. Now PBSL. Why did we name it PBSL and not PSL? I have no idea. Well, now we get some estimates. And on average, our probing sequence length is 206, which is pretty bad. And this already reveals why our code is so slow. PBSL. This already reveals why our code is so notoriously slow, because every time we try to update our values, we have to, on average, compare our city name against 206 other city names. Now I will make myself a cup of tea and then we're gonna do something about this. Well, first also just check results.csv and go into Zurich. Zurich is probably not a good idea. How do you do a vertical split in NeoVim again? V-split, nice. And base, and go to the end. Here we have, where is it? Do we have Berlin in here? Oh yeah, we do. Okay, Berlin. So this is the same. Okay. So, we have seen our average probing sequence length is 206. Now, do we also want to sort of report the standard deviation on this? Maybe. But for this we have to sort of do a trick. Let's see. So let's also report the standard deviation. I think this is a cool thing to do. Debug info. Let's say PBSL mean and PBSL STD. Now there is an algorithm for incrementally updating the mean and standard deviation, which is called the Welford algorithm. I don't recall this completely. Let's see. See how it works again. So to pass here Welford algorithm. Now we have our probing. Let's close this. OBRC debug. Now we don't do this anymore. This stuff, let's not do it like this. We need a count as well. So the hit count we can keep. All right, so delta. This is it has to be an F64. Delta. Oh, we first increment the count. Okay, debug info dot hit PBSL hit count plus plus. Delta is equal to the new value, so the difference between the old mean and, let's just say, okay, F64 old mean is equal debug info dot PBSL mean, and maybe also this is the variance, right? That's okay. So we measure the difference, which is the new value, so the PBSL minus the old mean. So this also has to be casted to an F64. And then we divide, we say F64 new mean is equal to old mean plus, we can do it like this. Our old mean plus delta over the debug info dot PBSL hit count plus plus, not plus plus. F64. Then we have the new mean, and with the new mean we can get the second delta is the PBSL minus the new mean, and then we multiply F64 M2, the delta times delta 2, and yeah, M2 is the, I think M2 is the variance. Oh yeah, okay. Wait. Okay. Do we have to divide? Finalize. Okay, so let's call this debug info. Where is it? Here, PBSL M2. PBSL blah blah blah. Oh man. Okay, we delete this and say debug info dot pbsl mean is equal to new mean, and debug info dot pbsl m2 is equal to m2. I hope this is correct. Well, for its algorithm for incremental mean and standard deviation or variance. Okay, so let's retrieve the. Okay, so f6 for pbsl mean is equal to debug info dot pbsl mean, and f64 pbsl variance is equal to debug info dot pbsl m2 over debug info dot pbsl hit count. F64. And then we can report average, so pbsl mu. How do we get a mu symbol? So mu let's call this mu, and percent to f variance, and then pbsl mean and pbsl var. Now hopefully we see similar numbers like 206, otherwise we have done something wrong. Let's see. If we don't see a 206 for the mean, then the algorithm we have implemented is wrong. Oh, the variance is very low. I wonder if that is even true. Why is the variance this low? PBSL M2. How do we initialize these? Yeah, because I have made a mistake, it is plus equals. Is this correct? This is not correct. Delta times delta. I mean, this cannot be true. 14,000? Are you kidding me? I think we have how do we initialize? Yeah, for n greater 1. The problem is that we initialize this incorrectly. I think the problem is that we initialize this incorrectly. So let's say if debug info.pbsl hit count is equal to 0, he would just say debug info.pbsl mean is equal to pbsl. And I don't know how we initialize the standard deviation. Should we ask, how do we initialize M2? Like, is there something on initialization? Nope. How's it initialized? M2. Yeah, I think Welford's algorithm initialization. How to initialize Welford's algorithm. Oh man. How do you initialize? I know we have to set the mean, but how do we set the standard deviation? Do we even do it? Let's see. Let's see. Let's ask Gemini. How do I initialize this code for updating the mean and standard deviation incrementally correctly? Should be initialized like this. No, this is not true. I think this is not true. Like, let's use, oh my goodness. Review this incremental mean and standard deviation update algorithm. It is initially 0 for mean, STD, and count. Like, how can this be correct? This is not correct. Like a variance of 14,202? No way. No way. No way. What is the bug? What is the bug? Old mean is 0. So this will... Why is this variance? Is it not possible to calculate this variance? The variance like this? I don't know. But this is not plausible. Or is it? I mean, what is the square root of this? What is 14,202? How do we do square root here? Oh my goodness. Does Python have math.square root? Import math.square root of 4. Oh yeah, it does have it. So 14,202. 337 is the standard deviation. So this could be true. We have Intel Intrinsics guide. We have the instruction. Oh man, come on. Square root. We have the square root instruction. Square root SD. Square root SD. Compute the square root of the lower double precision. Why does it take 2? Lower double precision floating point element in B. And copy the upper elements from A to the upper element of dest. What? Alright, so we could we could use math. But I want to use the square root instruction here. So where do we do var? Let's do f64 PVSL standard deviation is equal to square root single double precision, and it does it of a set single double. This is now some intrinsics code. So M128D. Let's pull this into our function. Let's just say f64 square root, and it takes an f64x, and we say M128D is reg is equal to set PD, no, SD, and x, and then we do mm0 set mm0. Can you do set packed double set pack double 1 0. I think this is correct. I don't know. And then we do square root single double precision and M128D result. It's not really the result. Reg result square root SD, and it takes it of A, which is the reg, or let's say it's the in, I don't know, reg and 0. And now we have to extract this extract. How do you extract lower 64-bit double from M128? Convert SD. Convert SD F64. So F64 result is equal to convert SD F64. So now we also have some intrinsics code here. I hope this is correct. So we first put this into a white register. We set the other register to 0, and then we perform the square root instruction on the reg. The other register will be copied into the upper 64 bits, and then we just extract the lowest 64 bits and return a result. Now var let's do standard. So this is square root PBSL var PBSL std. Let's see if this works. Oops. So we should expect something like 337 now. Nope. Okay. Our square root is wrong. Intel intrinsics square root single double square root of the lower double precision 64-bit floating point element of B 0 and reg. It's the other way around. And 119? Let's also print the variance. I don't trust my square root function here. So %.2f var PBSL var yeah, this is weird. Square root set is this an intrinsic implementation of the square root function on x64 correct? Is incorrect. Handles this argument, though it might appear to work in some specific context by accident. Computes the square root of the lower double precision floating point value in parameter b. But it populates the upper bits of the result register using the values from parameter a. This actually calculates square root of x correctly in the lower 64 bits, but it explicitly copies the upper 64 bits from a 0 register into result. While this works if you only care about the lower 64 bits, which extracts, it is unconventional and potentially inefficient. When you use it, usually when using scalar instructions, you pass the same register for both arguments if you don't need to preserve other data. Okay, so we can put 2 times the reg. Didn't know you can do that. But still, it shouldn't change the result, right? Did I type something wrong? For import math dot square root of 14 to 10. Okay, I typed something wrong. So this is correct, in fact. The standard deviation is just that. Well, so this works. We could also do this in assembly, actually. But let's not bother with that. So underscore square root. Let's not print the variance. Let's do it nice. Maybe this looks nice. I don't know. PBSL var, let's just discard that. We're spending so much time on useless stuff, but that's okay. Yeah, this looks ugly, but it's okay. So we have a mean probing sequence length of 206 and the standard deviation is 119. Great. So according to the sigma rule, normal distribution, we have 68% of our probing sequences are between 100 and 300 approximately. Yeah. How long is the longest probing sequence? Probably result.csv. We have 414, so it cannot be longer than 414. Yeah. Great. So this is also now in our code. Let's add another new line here. I don't know. Yeah. See, it's a little bit messed up because the threads are interleaving here. It's also not so nice. So maybe let's do it on a single thread again. Lane count. I don't know. How long does it take in a single thread? In debug mode. We can also maybe look at what this compiles into. So let's go into godbolt.org. Let's select the C programming language. The C programming language. Let's activate the Vim mode and paste our code here. No, it doesn't work. So let's just write it again. F64 is now type def double F64. Let's also just quickly pound include x86 intrin.h. Next thing would be to define our square root function. Square root, and square root takes an input f64x. Now we have to convert this, because of the way the intrinsics works, into this register, white register type, and this is our reg, which will now be set single double precision x. So the reg will now contain the lowest 64 bits will now contain x. Now what we can do now is use square root single double precision, and with the reg and reg, what this does, it computes the square root of the lower 64 bits of reg and copies the upper 64 bits into the result. And this is we can just assign it to reg, and then we can say f64 result is equal to convert sd f64. So convert the single double precision register into an f64 reg. This is just because we have some types in C, and that is that. Now you can see that the compiler is inserting some weird instruction here. So let's do, oh no, not ARM. Clang, where is it? x86-64 clang. Now the compiler is inserting some some instructions here, which I don't know why it does it. But here you can see the actual square root is the instruction of XMM1 and XMM0. So if we, for example, provide a 1 here, we see this compiles into a single instruction, because the calling convention tells us that X is already coming in XMM0, and then we can directly do square root SD, the square root SD instruction, and return, because the return value is also in XMM0 due to the calling convention. Now you can see that removing this instruction, this compiler flag adds a couple of instructions, and this is why you probably want to turn on optimizations. Yeah, and this is also why it's so much slower without them. Yeah. Yeah, I don't know if my chat actually works. My chat is broken. I hope I didn't miss any messages, but I think somehow it doesn't show me. Somehow it does not show me the messages. I don't know. Yeah. So this is what eventually our square root instruction will compile to. We can also check this in the debugger. Like if we say build, and we now compile this with debug flags and O1, and build this, and now we want to create a breakpoint in _square root. Let's create a breakpoint and let's run this. You get the same result with GCC fast optimizations using math.h square root. Yeah, of course we would get that. That's true, but we can also do intrinsics, yeah. So what you mean is basically, okay, use math.h, the built-in math library, and just call square root on x, and the same thing. Let's see. Well, interestingly, it adds some instructions here. Ah, of course it does, because we cannot call square root on 0, and we're currently not checking that. So our old code is actually wrong, because the correct code, let's call this square root hours, and call square root on x. I wonder why it does. Yeah, it does a call. Why does it do a call? Like, can it not inline that? GCC. Or is that not possible in Godbolt? I don't know. Ooh. Oh, fast. Oh, I returned X. That's bad. Yeah, you're right. We get the same result, but theoretically we should check, right? Theoretically we should check if X is 0, it should fail, but yeah, okay. That's actually interesting. Like, and what is the difference between O3 and O fast? Is O fast like doing some math, some assumptions on the math? GCC O fast. Okay. And GCC. Okay, I don't know how you do this. Help. I have no idea how you do this. What's the difference between GCC difference between O3 and O fast? OFast enables optimizations which violate requirements of C standard for floating point semantics. I see. So this is why also why Clang puts this. Yeah. As you can see, it clears the XMM1 register. Then it compares the XMM0 with 0. So it checks whether it's 0. If it's 0, it com_i sets a 0 flag, jump above. If it's above 0, and because we can we also cannot call the square root obviously on negative numbers. And yeah, can we? No. And if it's above 0, jump above, we no, jump. Doesn't even say, right? JA jump square root. What's JA? Thought it was, yeah, jump if above. Jump if above the. Okay. Jump square root. Where does this jump? Okay. Maybe I'm just too stupid to read this, but it's okay. My chat is so broken. I don't know. It does not show the messages. Come on. One second. Let's fix this chat thing, because I think maybe someone wrote something to the chat. Yeah, but you can also not get the chat history, right? Yeah, so we're screwed. I don't know, how can you pop up the oh, chat. Reject. Okay, I think I now have the chat. There is a chat. At least the Twitch chat. Okay. So jump above. It compares. It compares the first to the second. So it does a yeah. Because it does it this way. If it is negative, it jumps here, right? Is it true? But where is square root? Where is that? What does that do? Jump square root. Whatever. I. All right. Yeah, this is our version. It's buggy because we have to check. So if this can only be done if x is greater than 0. And now, oh, let's see what GCC does now. So now it looks pretty similar, right? We clear this register, then we compare and jump branch equal. And now below equal, jump below equal. So if we're less than or equal to 0, we go here. We clear the XMM0 and return. Okay. looks a little bit different. So is it less than or equal to 0? Whatever. Let's not get stuck on this stuff. It calls glibc square root because it sets ernl. You can remove that specific. Oh, why is my Chrome now gone again? Now it's gone, right? Oh no, it's not gone. So you're saying it calls glibc square root. F unsafe math optimizations. Man, you know your flags. F unsafe math optimizations. Okay, no, it's still there. It doesn't matter. Okay, so why are we doing all of this? I don't know why. We just wanted to get to know how the mean and standard deviation of the probing sequence length is. How long? And then we went down a rabbit hole somehow. Yeah, let's see if it works. I don't know. Okay. So this is again on one thread, right? Lane count. Lane count is 1. Okay, one thread. Yeah, we have a average probing sequence length of 206 and a standard deviation of 119. Now, and our results are correctly stored, hopefully. So if we, for v split, and go into, I don't know why it does this, baseline small, and we check Berlin, we have the same kind of thing. I mean, we'd have to check all of this. We could also write some code for that, but let's not bother with that. Okay. So the next thing we might want to do is get down the average probing sequence length. By using a better hash function. Our hash function just returns 0. Now, I do not have that much experience with hash functions. It's actually no math, or no. Yeah. Okay, but then it completely optimizes it away, okay. Whatever. Oh, fast. I didn't know that. That's actually pretty cool. And here it does something completely different. It eliminates the branches. Whatever. Okay, let's do some, how do we determine our hash given the bytes that are representing the city name and their length? I have not that much experience with hash functions. I think we should use maybe we just use something that's out of the box for now. We can use XX hash by just copying. I mean, is that cheating? I don't know. Let's download. This doesn't work, right? How do you do a raw clone of these files? I mean, we could theoretically go here, git clone this. So this is a hash function someone else has written, and move access hash dot h here dot c here, and rmrf access hash. Now we can now include the header xx hash dot h, and we have to also add the C file to our compilation. So does this build without using it? Yes, it does. Now xx hash, I don't recall what the functions are called. Oh, it's just the header. It just has just the header, okay. So then we don't need this stuff. All right, so that's nice, a single header code. So xx hash, oh, did I just remove the header? I did. Oh no, no. So we have to git clone it again. Hash dot h here. Okay. So let's see, xx hash. What was it called again? xx u32. I do not remember. xx, does it say maybe in the documentation? Small data. Create state, no. It's 64-bit, xx hash functions. I thought it had a 32-bit one as well. XXH32. Let's just see if we can call this 1brc.c. Okay, in our hash function, we just call xxh32 with the bytes and the length, and get a u32 hash or digest. Let's see. Okay, it wants something else. A seed. It wants a seed. I don't know what a good seed is. Initialize state with selected seed. What? I mean, I don't know. Let's just use 0. Okay. Unrefined reference to XSH32. Ooh, okay. So maybe we do need the. Maybe we do need the file. Okay. Maybe we do need. Okay, so now it works. What happens if we just execute this? This seems a little bit suspicious. We now have a PBSL of 0 in the mean and 0.05 in the standard deviation. Let's RM results. I've cloned this so many times by now. Result.csv. Let's run it again. Okay, so this seems odd. We have drastically reduced it. Let's also see if the results are correct. It seems so. Baseline. Yeah, it's still correct. Like, let's check another city as well, like Zagreb. Yeah. Wow. You can see by just removing, by just getting a better hash function and reducing the linear probing sequence on average drastically, we can get the time down quite. We can get the time down by quite a bit. Let's see. Yeah, I don't know what XX hash 32 is doing under the hood, to be honest. It uses AVX2. I mean, we haven't even compiled this with AVX2 support, right? We can also MAVX2 because our processor has it. Let's see. So it's even a little bit faster. As you can see, we're now only spending. Now, where do we spend our time then? Let's add another prof. Now you can see we only capture 36% of execution time now. That's bad. So an entry point. We have some. I mean, here we call profiler init. Profiler init captures this until we hit profiler report. So what we're not doing, but this can't really be. I mean, we could also profile find character profile function by adding this here. Profile end, then building again. And we're spending quite some time in find character. As you can see, this is still not 100%. Profile init. Find character, insert record. The barrier, I don't know if the barrier takes a lot of time. I don't know. But theoretically we should see, like this is 40, this is 50. We only see 50%. Where are the other 50%? Profiler init. Profiler report. Probably the other the other 50% are spent in our profiling code. That would be bad. So we have some, so enter zone, calls a function get zone. Get zone is pretty stupid because get zone goes through all of the zones, which is a global variable, like profile zone, and it goes through all of the zones and it checks whether the names match. For obvious reasons, this is not the best way of doing it. So we should also implement this similar to the hash map. Let's call this get or insert zone. And let's make this a hash map. So let's call XSH32 directly here. We don't know the length, so we have to kind of do this. So name length, and then name length, and 0. Okay, and then we get the zone. Yeah, here we run into the same problem. Let's just say this is I or zone IDX I zone IDX digest plus I. And now we need to know how many zones we have. Profile zone. It was a power of 2. Zone count. Let's make a quick macro that gets the size of an array. Define array length as the size of the array over the size of the first element of the array. Get or insert zone. Okay. Now, and this together with, I mean, we can just do zone count -1. Then we index it with the zone index. So let's see. Get zone, get or insert zone. Zone okay. Compile times went a little bit up. All right, now we see what? Now we see a null zone. Oh no, this is bad. Get or insert zone. I feel like we have a bug in here. Like, how much time do we spend in? What if we just what if we disable all that we have done here? That's like 16%, 10%. This can't be true. And why is there a null zone now? Why is there a null zone? Get or insert. What did I do? XXH32. Is this correct? Seed. I don't know. Zone. Profile zones. Sterling. You already have that here. Name. Length. I feel like we're having some troubles here. We get a null zone. Oh, I know why. Because in profiler report, we have to now go through. Yeah, this doesn't make sense. Okay, so we have to go through all of the zones. Zone count now. And this is the zone. And if the zone, if the name is set, I don't care. Like, let's do just the name. We print this. All right, so now we, okay, so parse temperature was missing. That was why we were not seeing this, but still, we are missing a lot of time here. Is our profiling causing all this? Who knows? If we need an efficient way to turn off the profiler. Okay, so profiler init. Let's do this. Profiler report. Enter zone. I mean, theoretically, we have to find this here. So if prof enable, we pound define profiler init to profiler init. We pound define profiler report to profiler report. And we just pound define profiler init to empty and profiler report to empty. Now, build expected expression. Come on. Oh, CPU. Yeah, you know what? Just do VA args. Okay. Ooh. If we disable the profiler, it executes in 0.48 seconds. That means if we're going to build and say -d prof enable, which will enable the profiler, shit. Expected expression. Oh man, why does this have something wrong here? 577. How do you VAX goes on the left side? Ah, shit. Oh my goodness. Oh my god. I forgot that. Thank you. Now it works. Yeah, you can see, oh my god, we spent suddenly 2.2 seconds. Like 1.8 seconds just profiling. Like, is it a problem? Probably. Oh no. Yeah. It's because of the string comparisons. Oh my god. Probably because of the string comparisons. Do we care about this? I don't know. I mean, it's pretty misleading that this tells us, yeah, okay, if I add this up, man, it's just 50%. So maybe we shouldn't do it like this. Okay, let's... I mean, it's okay. Okay, it's even worse if we... It's even worse if we go wide. Wonder why. So 1.6 seconds, and with profiling disabled... Oh no, 4. And with profiling disabled, one second in the profiler. That's bad. Oh, okay. Maybe also here, I don't know. I mean, if we even disable this, it's a little bit faster. Okay. So I wonder, how much time does it take? How much time does it take on the big file now? Oh shit. No, I opened the measurements on text. We have to end any of them now, I guess. I mean in one brc.c. In measurements. Let's do the big file. Let's do the big file. Man, what is this? .7 seconds. Okay. We are in bash again. It crashed. Okay, let's do the full thing. Let's go 03 and just see how, and without the debug flags, the debug information. Let's just see how long it takes. Okay, so in our profiling code and estimate CPU frequency, we wait 100 milliseconds. So yeah, but that shouldn't be that bad. So 8.9 seconds. Okay. So we went down from 6 minutes to 8.9 seconds. Okay, I don't know what I did there. So let's enable the profiling again. Let's go into the build. I mean, we're almost quite there where we want it to be. Let's add debug symbols. This. Let's -d prof enable and -d obrc debug. This is on the big file now again. Let's see. It probably will take a little bit longer. Oof. Okay, so we went from a point where we spent all of our time in in insert record, because we were basically linear probing all the time, to a situation where it's almost equal. I don't know what's happening now. Let's see, lane count. Why does it take so long now? It took 8 seconds, and with profiling enabled, maybe it's because of this also. And with profiling enabled, it takes over a minute or what? Like, this is this is not acceptable. We then probably have to rethink how we profile. Then we we cannot do these checks. Like, that's not acceptable. Like, just turning on the profile, it takes an eternity. That's not good. That is not good. So let's rethink this. I mean, we have pretty much predefined zones. Like, look at this. Holy shit. I mean, we could use something like perf, but I want to use this. I want to do it like this. Yeah. Oh God. Takes forever. Oh man, that's not acceptable. Let's go like this. The profiling overhead is too big. That's just so fascinating. And I don't really know why it's so slow. Let's add some zones. This is wild. Like, what the heck? Okay, so what if we predefine the zones? So we disregard the name and predefine zones. I really liked how we did this. Like, that you can just do profile function. It's pretty cool. And profile scope. Maybe there's a better way of doing this in C and achieving the same kind of flexibility, but okay, let's say something. Let's do it a little bit differently. Let's have an enum profile zones, and here we have our parse temperature. Or can we do it like a little bit differently? I mean, theoretically we could. I would have to think about this, how we can do this. I mean, something is wrong here. Like, this was a big file, right? It took 2 minutes. That's not true. Get or insert zone. Takes the name and the name length. Probably this is a little bit stupid because it does stir length each time. That's probably stupid. So let's say profile zone. Let's say this is a string name, and get or insert zone. What we do is, okay, I think we had some macro for strings. Stir. Didn't we have a macro for this? Like, did we have struct string? How to find string literal string dot pointer literal dot length size of literal and profile function now get or insert zone now needs a string. This and now needs a string. Like this is, there's no way around this. Name dot pointer name dot length and then string equal and name and zone name get or insert zone. Now enter zone takes a string. Enter zone is called here name. String name. String func. Does this work? Woo! Where's our string macro? String u8 star. Let's see, root string statement requires if no which line was it? 258. Zone name dot pointer. Zone name dot star s. Zone name dot length. Zone name dot pointer. We have to cast this to an int. Fine. Or I32. All right. So now it builds. I feel like it's still pretty bad. I feel like this doesn't give us a major speed up in the profiling. And we have to do a hard-coded version of this, which is not nice, but whatever. Yeah, it's still taking very long. It's still taking way too long. Like if we build with not prof enable, when it's done, you can see that that it's a nightmare. You can see that it's nightmare. Yeah. Trying to find a zone every time, not a good idea. Not a good idea. Okay. How can we fix this? Okay, first we just verify that we didn't do anything stupid and just build it with prof enable not set and time it again. And it takes 9 seconds. Let's do obrc debug for quickly verifying that the results are correct. All right. Yeah, that doesn't really take any time somehow. And results.csv, no, let's rm results.csv. I'm impressed that this takes barely any time. Let's run it again. Let's see the split, and baseline is now the correct thing. Let's look at Berlin, and we're seeing different times, different results. Is this still the old thing? Which file are we processing? Which file are we processing? Measurements.txt. Now that's bad. We're seeing incorrect results. That's not good. Oh, why are we seeing incorrect results? No, not open this. Result. Okay, let's restart any of them. Just, oh, I did remove it again. Let's just quickly rule out that we didn't screw, that it wasn't a cached file. Ah, we removed it. Ah, come on. Where? Where's the result file? Come on. It should have created one. OBRC debug. Why is it not creating one? Let's pack a syntax error in here. Okay, apparently it's compiled. Why is it not creating the file? Now it created the file. Berlin. This looks better. V split. Baseline. Berlin. Yeah, so this is correct. Okay. So we basically have a very bad profiler that takes up all of our time. That's okay. I mean, certainly it's not okay, but we can fix it. Hopefully. Okay, parse temperature. Let's do it very naively. Insert record. What did we have as well? We had... do we want to do this somewhere else? Hello, hope you guys are having a fun day. Yeah, sure. I hope you're having one as well. Let's make a macro. Count define scope with a name that creates a static profile scope, and then name prof scope name with the dot names equal to string name name, then all the other stuff is 0. I think you can just do that. Okay, or define scope, yeah, whatever. And then enter begin profile name will do enter zone. Now let's create another version of this. Enter zone 2, and enter zone 2 gets a profile zone directly. So it doesn't have to do that. And begin profile now does an enter zone 2 with the prof scope concatenated with name, and end profile does just exit zone. Okay, now we replace profile function with begin zone find character and it was begin profile. I hope this does anything. End profile and begin profile parse temperature end profile and these we also want to put into here and also here. Okay. So that they do nothing. Now this is pretty confusing, but begin profile. Profile function. Begin profile insert record. Oh, we could also do, no, forget about it. And profile. This is very messy. Begin profile join record maps and profile. We also have profile scope, which we replace with begin profile get mean. I mean, we could do this profile scope let's just do it like this. Yeah, I'm trying to get some metrics, but the problem is that our current way of getting the metrics, which is way too slow. It's slowing us it's slowing us down. The profiling code is slowing us down quite significantly. And yeah, that's that. Yeah, it's quite a situation, you know. Okay, so I'm now trying to hard code it. Profile scope. I think that was it. Now we just have to define all of the scopes. Or let's call this define zone. Now we have to collect all of the begin zones we had, which is also not that nice. We have to clean this stuff up. It's like, oh, define zone. So we had parse temperature. We also had insert record. We had enter zone 2. This has to be a reference. Define zone get mean. Define zone join record maps. Begin find character. Yeah, find character is missing. All right. Define zone. Okay. So this. Oh yeah, define zone. Let's see if that's any better. So our code obrc debug. Our code without profiling takes how long? Oh, it's segmentation faults. That's also very good. Great. Okay, so we introduced a bug. We have introduced a bug. Profile function. We have not used that. End profile. Yep, we have introduced this bug with this. I think this should now work. So without debugging and full optimizations turned on, let's build it again. On 1brc, oh no, 1brc.c, lane count, we have 4 threads at the moment, and we take like 9 seconds. With the XX hash 32 hash function, we get a mean probing sequence of 0 and a PBSL. Let's actually get some more numbers here. 5. So a mean probing sequence length of 0.02 and a standard deviation of 0.04. So we're not doing a lot of collisions, which is good. Now, with profiler turned on, dprof enable, we build it, we get an error. Of course we get an error because define zone is stupid. Define zone should have this profile scope, and it misses a semi. What? Okay, do we have to put all? Yeah, maybe we have to put all of them in there. Where do we have the struct definition here? Just take all of them, just put them in here. SU64 dot. Dang it, it has a space. Whatever. We could have done a better macro here. Whatever. Let's just do it like this. it still expects a semicolon. Oh my god. Is it because I added? What are you doing? Oh my goodness, we missed those. Oh my goodness. Multi-line macros. Whew. Use of undeclared identifier. Of course. Now we're getting all of the goodness C has to offer. Struct profile zone. We have to pull this up. Or pull those down. This is also possible. Now, enter zone. Enter zone. Profile scope. Enter zone takes a reference. And we also have to use enter zone 2. Now, still a bunch of errors. Profile zone declared here. Oh my goodness, it's called profile zone. I'm mixing those two up all the time. Okay, so now it's still not working. Did you mean profile zone? Of course I meant profile zone. Still, profile scope. Where did we, why? Why did I think this was a good idea? And it's still not working. Okay. Field designator polish temperature does not refer to any field in type. What are you trying to tell me? What are you trying to tell me? Oh, I love macros. I love them. I thought this would just work. So this should do a concatenation. Why is this macro incorrect? Do we have to add a space here? I don't know. No. Oh my goodness. Because this is also name. Oh no. Okay, zone name. That's a bad one. Yep. No space. You cannot do a space here. That's not allowed. Backslash a new line separated by space. That's not allowed. That is not allowed. Oh god. Okay, so now I forgot how long it took in the first place. I forgot how long it took without the profiler. So great, it took 9.3 seconds. Let's add debug symbols. See if it's still kind of the same. Okay, 9.3 seconds. I mean, that's not That's not a good number. That's not a good metric here. We should do it a little bit differently, but let's enable our profiler, prof enable, and let's see how bad it gets. I wonder if it's because of one specific thing we did, which is problematic for our code. Okay. Maybe it wasn't even the comparison. No. Is the profiling overhead so big? We should look at the assembly for this. We should be looking at the assembly. Yeah, let this run, but as you can see, it takes significantly longer. Profile the profiler. Yeah, we should. God dang it. Why is this so bad? I mean, you can't be doing this to me. Now we hard-coded everything in there. And yeah. Now the problem, one problem is probably because, so one problem the profiler causes is probably that we use this RDTSC, which is a hard-coded, which we defined in our assembly file here as RDTSC shift left RDX by 32 or RAX and RDX and then return. It probably can't be inlined if we do it like this. But that can't, I mean, just because it can't inline this can't cause this slowdown. Like, this takes minutes instead of 10 seconds. Okay, let's remove some scopes here. Maybe it's so this, let's just remove that. Parse temperature, that would be nice if we had that. Inside record, that would be nice if we had that. Begin profile. Join record maps, that should be almost completely free. Okay, you know what? Let's go here. Build. Build has all of this enabled. That's good. Now enter zone 2. Enter zone 2. Let's make a breakpoint. And hello? That's still running here. Wait a second. Let's do this. Let's do this. Let's do this. And okay, find character. What are you telling me? It's not used, right? Yeah, it's not used. Whatever. Let's run it. No. So the debugger was running. I don't know if that caused any problems. Like maybe the port was hammered. I don't know. No, that can't be the problem. Okay, let's see. Let's just let it run one more time and then try to go in the debugger. Yeah, this is not good. This is not good. This takes way too long. Okay, so enter zone 2. Let's launch the debugger. I also hate that I have to do this in VS Code, but maybe you have something that's working better. The question is, does it even hit it? Like, is this even working if I enable O3? Does it work? I mean, I have debug symbols. Theoretically, it should. It doesn't seem so. It's very weird. It's very, very weird. Like, what is this? Why? Show me the disassembly. Why are you doing this to me? I mean, this works, but enter zone, is it maybe completely gone? Enter zone, please. Doesn't hit it. Okay. Let's don't optimize anything. Let's not optimize anything. Now we hit it. But now we can't. Oh my god. I mean, now we can see that this is a call. But we can't see it if we turn on optimizations. Dang it. Why? Is it because it inlines enter zone? Okay. So I have a... this is bad if we can't do that. I mean, I cannot do this. Like, we have to see the assembly. We have to see the assembly. Otherwise we're screwed. Like, how do we find the assembly? Ah, shit. I mean, this you can't read. Like, how do we get for optimized builds? How do we get the assembly? Like in a debugger, like I should be able to just put a breakpoint here and run the debugger. And And yeah. No. It won't let me do it. Oh my god. Like, can we do this somehow in LLDB? Maybe LLDB. 1BRC break. Break at enter zone 2. Run. Nope. Enter zone 2 is completely gone. It's completely gone. Can we break at something else, like break at parse temperature? Oops. That works. But enter zone 2? No. I won't let you do that. It's just gone. Can I prevent the compiler somehow from inlining this, or preserve at least the okay, parse. I mean, parse temperature has a call to enter zone, right? GNU no inline. We can try that. Okay, parse temperature should be going out. How do I step? Step instruction? Oh, no inline, okay. Okay, a bunch of moves, XOR, and here you can see it does a call. Call Q RDTSC. Probably because we have done this thing in assembly. So let's just replace our RDTSC calls with RDTSC or RDTSCP. RDTSC, RDTSC. And if that maybe does a difference, I think the intrinsic was RDTSC, right? Intel RDTSC single underscore, and here RDTSCP has double underscore. Okay, let's use RDTSCP. The main difference being that the out of order stuff doesn't affect it that much, I guess. If I had understood that correctly. Let's see. Oh, it takes an argument. That's bad. It takes... What? Copy the current 64-bit value of the processors into memory. Dang it. And also 42. 18 cycles. Oh my god. Okay. It takes 18 cycles. Okay, let's not do RETSCP, whatever. This is for the processor ID, right? Let's do this. RETSCP. No. RETSCP. RETSC. Global. There we go. Build. Let's see. So, if we now do this and break at parse temperature, run. Here you can see it can successfully inline the stuff. And here you see we have the RDTSC instruction. Then we have a shift left quad word RDX by 0x20, which is 32. And then we OR the quad words together, RAX and RDX. And yeah. And we store it. We store it somewhere. We store it in prof scope parse temperature plus 16. And we add it onto that stuff. So maybe, just maybe, this helps us a little bit out. So by using the intrinsic, we can basically ensure that it's being inlined. Yeah. So it's probably not a good idea to do the thing I did here, like define an assembly function, because Clang cannot inline this. I mean, if we can get away with this if we don't compile this with NASM, but provide the assembly file directly to Clang. But I don't know how that works. You can probably parse a flag here because I also use a different syntax. I use the Intel syntax. I think you have to do dot global dot section, and you have to prefix it with an underscore. It will never inline assembly, even if I let it. I mean, even if I put the assembly file here as a source file, it will still not inline it. Clang assembler Intel syntax flag. MASM Intel. Let's try that. So let's use the ASM and let's not use this. Shebang user bin bash. You can use inline assembly with a pound define. Yeah, I know I can use it. I hate inline assembly. MASM Intel. Okay, but it's still taking like 2 minutes. And our profile report is broken. Yeah, that's true, actually. Oh my goodness. Okay, we also have to fix, but is it worth it though? Is it worth it fixing this instead of just using the string compare? It's probably a little bit faster. Okay, so profiler report. We had the zones. We have to redefine the zones. Where are the program zones? Program zones. Profile zones. Profile zone count. Let's do it like this. And we have all of our zones. This is not good. This is not good. Let's put them up here, directly next to each other. And profile zones parse prof. I called it prof scope, right? Oh man. Parse temperature. This is very bad. Oh god. Great code, as you can see. This is very nice. F. Join record maps. Find character. Okay. Profile zones. Okay. Profile report. This will be the zone. This will also break other code, like get zone, get or insert zone. I mean, this is broken anyway, so yeah. I should start using version control. Okay, unknown token and expression. Now, we're now trying to compile this with Clang. Asm. Does it not know custom? Let's just use custom. Shit. How do you do comments? Whatever, just delete them. Okay, profile report. So this is not zone count, but array length of profile zones. Hi. How are you going? Oh, I'm getting along. How are you doing? We're struggling because our profile instrumentation profile code has such a huge overhead. It literally takes us from executing the code in 9 seconds to executing it in a whopping 2 minutes or so. Well, let's see how it's now. Oh yeah, so somehow it was broken. I don't know. Yeah, I didn't read chat yesterday. That's true. I'm sorry. I'm sorry. That's nice. Yeah, so let's see if our profile is at least now not broken anymore. And oh man, I'm not a god. I'm by no means a god. You just have to put some practice in. Like, I am no special. You can get at least as fast as me. But you don't have to, like, it doesn't really matter. So it's still, I want to see, like, has Agner fork instruction latency table. How long, like, is it like for our CPU? Can we see that maybe? Or no clock is used, blah. How the values are measured. Oh my goodness. Let's see. AMD K7. What I think microprocessors tested. Okay, we have a Ryzen Zen 1. This is probably the most approximately. Oh yeah, thank you for pointing that out. Let's see. Ryzen, we have a Zen Plus. We have a Ryzen 5 2600. Probably the thing that comes most closely to this is this one. So let's look at the instruction latency table for that. It's actually pretty cool that he has that. So K8, K10, Bulldozer, Pile Driver, oh my goodness, this is huge. Can we quickly search this, like Zen or AMD Zen? Ah, we were almost there. Okay, Zen 1. Let's see, RDTSC. Where is it? LZ count. Oh, come on. Nope. Where is it? Integer vector instructions? No. Arithmetic instructions? Logic, string, encryption, other. Where's RDTC? Oh god. Can I search on a page? No, not excavator. Zen 1. Where is it? Prefetch. Where is it? Oh no. So it's starting at page 86. Can I somehow scan forward? 86, 86. No. '91. This is the one, right? Zen 1. Here we go. Other. So what is what? Ops, latency, reciprocal throughput. Okay. Other RDT speed. So this was latency, right? We only have a latency number. 37 instructions. 37 cycles for RDTC. Oh man, that's quite That's quite an instruction. I mean, it's better than going into kernel space, but as you can see, 2 minutes. Wow, that's impressive. But now we can see the report. Yeah. I mean, we're calling RDTSC a billion times. No, not a billion times. We're calling it. How many zones do we have? Like here, I mean, we have one. We are not using one of them, so we have 4 zones. So this zone is executed every line. This one is executed every line. So only 2. So we are executing the RDTSC instruction 4 billion times. I don't know if the processor likes this. Okay, let's get a little bit. Let's reduce the amount of lines to 10 million. That's a lot faster. Let's introduce find character again. Begin profile find character and profile. What we could also do is this function, but whatever. So let's see. So on 10 million lines, this is very, because we are executing this on multiple threads, this output is not very nice, but we should also report the thread number. Let's see. Or we join those together, I don't know. I mean, whatever. Reprofile, okay, here, and then there's the, put the lane IDX here as well. All right. And as you can, no, you can't see it. What the heck? Didn't I save the file? Use of undeclared. Oh shit. All right. U32 lane IDX. Okay, now we also see which processor we are running on, and as you can see, yeah, join record maps is only executed on processor 0, and it takes 27 milliseconds approximately. I didn't think that. I mean, I also had. I wasn't expecting that RDTSC is causing that much of a slowdown, but probably also. I mean, let's do a back of the envelope calculation. Like, let's say our Zen plus architecture. I don't really know how many RDTSC it can, how many ports it has. Like, let's say it has 1 port to do RDTSC. And we can only do 1 RDTSC per cycle. therefore. Now, 37 cycles. We had done this 4 billion times. 4 times 1 billion. That's this number. Now we are executing at 3.4 gigahertz. 3. So that's already 43 seconds. That explains something. Now we also do shift left and an OR. Yeah, but at this scale, this just causes major slowdowns if you use these instructions. Yeah, but I think it's not really that of a problem. If we were to use RDT SCP, which, yeah, this has even more, and RDPMC takes only 20 cycles. But this requires some shenanigans with perf, I think, and I don't know how to do that. But we have to get into that to see the cache misses and stuff like that. We need to use RDPMC with the perf module, where we will see how that works. Yeah, and these CRC instructions for cryptography, we probably want to use them as well for the hash. Yeah, this is also a thing. We haven't profiled our hash. Like, how much time do we spend in hashing? Hash. Like, let's say profile, begin profile hash and profile. And then we also need a prof scope. No, define zone. Define zone hash prof scope hash. That's very ugly. Build. All right, what are we seeing? Oh my god, we're spending 12% in hash. If we at 101%. What? Like, this is no good. This is no good. What am I doing? It's 100%. Sure. Where am I calling profiler in it? Here. Profiler report. Like, this is bad. How can we spend 100%, more than 100% in a function? That's not possible. Oh. What? That wasn't the case. What did we change? Oh, we were always seeing these numbers here. Here we did see different numbers. What did I change? I mean, it can't be just the hash. Prof hash. that's the bug, I don't get it. Oh my goodness, it's because I do end profile. Or is it? No, end profile. No, this is correct. No, hash. If that's for real the problem, I don't know what's happening. These numbers seem to be completely random now, or are they? I mean, now I don't know if I can trust these numbers. Like, I removed... What is this? Oh my goodness, do you know why? Oh my god. I have made a dumb mistake. I've made a dumb mistake because these things, they were local to a thread. Each thread had them. Now, define zone does some stupid stuff. It does not define them as thread local. That probably fixes it. Initializer element is not a compile time constant. What? Initializer name is not a compile time constant. What? And now that... You can't be telling me that this is now breaking. So by adding thread here, this breaks. How is that possible? Do we have to add thread here as well? Duplicate thread. Are you kidding me? I don't really understand why. Initializer element is not a compile time constant. Okay. So maybe we can't do it like this. Should we ask Gemini whether we can do this stuff? Or should we just should we surrender for today? And come back tomorrow. Dang it. Dang it, I didn't expect that. Why? I want these to be thread local. I think I want that. I don't know how I do this though. don't know how I do this. Does anyone have an idea? I do not have an idea to how to fix this. Zone. Okay, so I asked Gemini, and I don't know if I understand it correctly. Let's see. An automated approach, X macros. If you want to avoid manually updating the array every time you add a zone, use an X macro. This ensures your definitions and your array stay in sync automatically. Okay. So pound define zone list as X parse temperature, parse insert record, get mean, find character. Pound define X name what the heck? And this doesn't seem like it works, right? Declare the array size. What? X name plus 1? What the heck? I don't understand this a single bit. Okay, maybe we add another hard-coded. Yeah. Okay. I don't really get the hacking it did there. We can just in profiler init profile zones. Let's just leave them empty and say zone count and pound define zone count 32. Oh god. Okay. Then delete this stuff. Then go into profiler init all of this stuff just to have man. Okay, and then insert. I put this at the end. Okay, we record a macro. We say profile zones at 0 is equal to this. We go to the end, delete this, go down, Q. Yeah, we forgot to go to the beginning. But whatever. Okay. Now, look at this. G Control A. Everything incremented. Let's see if it builds. Okay. Prof scope hash doesn't define zone. Define zone hash. Okay, so every time we add a zone now, we have to add it also segmentation fault. That's bad. Oh, I know why. Because our profiler report. God dang it. Zone count. Let's also static thread profile zone count. Let's say in profiler init, we set profile zone count. This is stupid. So much hard-coded stuff in here just to get that thing, because this now doesn't work. This is now profile zone count. Profiler zone count. Profiler zone count. Now we shouldn't get it. We should wait a second. We're still getting an error. Profile zone count. Profiler zone count. Profile zone count. Come on. Now it works. As you can see, it's completely fragmented. We should probably aggregate this onto a single thread. But yeah. We can also just reduce the lane count to 1. It takes basically the same time. That's pretty wild though. It takes this almost the same time. Like, what? All right, it's okay. It's okay. Okay, at least we have something we can work with now. I think so. I think we made some decent progress. Let's see, what did we have here? Like, fix the implementation so that we can support more than one thread. This we did. We scanned here through. If we are greater than 0, we see how many bytes are left. We find the first new line so that we can start at a fresh line, and we scanned from the end index to the next new line so that we know where our proper chunk end is. Yes, so this we did. And add debug information to the probing sequence code. We also did that. We also did this. Add a hash function and RETSCP we didn't do, but we probably don't do it because if we look at this table here, like 64 cycle latencies, I don't know if we want to do that, to be honest. Yeah, one thing that's still left is that we wanted to see, I mean, I had this custom RETSC here. I wonder why this still works. Like, how can it resolve the extern custom RETSC? Main custom RETSC. extern RDTS. If I do it like this, how? Okay, I almost thought, how can I resolve it? Okay, let's now see if it can inline the assembly function, if I pass the assembly function to Clang directly. Custom, extern, custom RETSC. So beforehand it wasn't able to do it. Start, let's see, end. And then elapsed and minus start and printf %lu, just that it is not optimized out. Well, did you mean custom RETSC? Yes, I did mean that. You are completely right. And let's see, so break, no, LDB 1BRC. Did we have optimizations on? Yes, we only 01. But let's see, break main, run, and step instruction, call queue. It calls. It still calls. Dang it. No, it still does a call. Okay. So yeah, we're not using it. Or can we somehow get it to inline it? I don't know. Maybe not. Maybe not so much. Yeah, interesting. I mean, we can use inline assembly and of course then it's inlined, but that's sad. Now we have to use intrinsics for that. Or really inline assembly. But I'm not really into that and I don't really know how it works, so we probably have to look that up. So do we have Git on the server? Yeah, okay. I don't know, should we use version control? Or just hack it together? All right, let's do a final run. Let's do a build with O3. Let's disable the profiling because it's so slow. And let's also just let's remove this from the compilation because it does nothing. 1BRC. Where's the extern? Let's remove that as well. Are you kidding me? Oh my god, what? Of course. Ugh. This is so ugly. Okay, now we don't do it on the small file. Measurements.txt. Okay, we built this And we also remove our result.csv. Let's run it. Nope. Time 1. Now let's increase the lane count from 1 to a whopping 6 threads. Let's build it again. Let's say time 1 BRC. And yeah, we should also remove like we should at least use our I don't know. In our build, let's also remove this here. OBRC debug, because we don't want these things here to be printed out. I mean, we can also now look into the results and v-split into this. Go here, then open baseline and see that they are the same. Barcelona. I'm seeing here Barcelona. And we get the same result. 69.3. Nice. Good. Now, if we really strip out everything and run this code, we can run this in 6.3 seconds, which is not that, it's not that fast, but it's also not that much, right? In the next streams, we're trying to push this number down by using the instrumentation profiler we have developed now, which is obviously not the latest and greatest stuff, but the prof enable, because if we run this with the profiling enabled and everything enabled, it takes an eternity. And the output is also not very nice, so maybe one thing we want to do is also aggregate them together, all the profiling outputs. But yeah. Also, it's so dark here. Let's turn on the light. As you can see, it's taking much longer than 6 seconds. Well, we can now use perf and a flame graph to see how much the profiling overhead is. But I don't know the commands for that. I would have to look them up. But as you can see, it's quite a lot. It's quite a lot. Is running forever. As you can see, 1 minute and 23 seconds. Now, let's create a quick difference between the two. So we have 1 minute and what? 1 minute and 33? What was it? 23. 1 minute and 23 versus 6 seconds. Like, this is ridiculous. And as you can see, we spent now, so last time we spent 84% in inside record. Now we only spent 27%, and which is the same as parse temperature. So now optimizing insert record is on par with optimizing parse temperature. So they're both worth investigating. also find character is a pretty big issue. Yeah. Oh yeah, hash. What's up with hash? Let's do it on a small measurements small. We haven't added hash. Hash. Let's add it again. So hash is also taking quite some time, which is only the XXH32. So we also have to get into hash functions with CRC32 instruction, probably. I wonder if CRC32 can also go wide. It doesn't seem so. But maybe XXH32 is faster all the time. Okay, so guys, I'm gonna go now because I have to make myself some food. Thank you for turning in, and yeah, I hope you maybe you learned something. And yeah, I wish you a very nice evening, or whatever your time zone now is, right? See you.